Alright, welcome to physical science. Alright, let's go over your homework first. So you have questions 9, 10, and think number 2. Alright, number 9. What is sublimation? Alright, this is whenever a solid changes directly into a gas. Be sure to mark that. So sublimation, or whenever it sublimes. This is whenever it changes directly from a solid into a gas. Alright, what is the state of matter in which atoms break down into charged particles? That is plasma. So make note of that. That's the fourth state of matter. It's the uncommon state though. Alright, think number 2. When lightning passes through the atmosphere, it can heat the air to 30,000 degrees Celsius. Then we find them as hot as the surface of the sun. Which state of matter would you expect to find the air in the path of the lightning bolt? So what state of matter would that be in? Solid, liquid, gas, or plasma? Right, plasma, because that's super hot. It will cause the air to break apart into its ions. Alright, you can go ahead and put that away. Alright, so I have your pages for your quiz today written on the board. So we've been going over these for a couple of days, so pages 99 through 107. So I'm going to say that you write down the bold terms and the definitions. I'm going to say twice, but use this to study. So don't just do it just to write them down, just to write them. Use it as you're going through to make sure that you're at least getting those bold terms and definitions. Now I'll review with you as well right before we take the quiz, but you want to use this time to the best of your ability so that way you can be using your time to study. So double check your knowledge of the terms and definitions. If you realize that you don't know a bold term, study it, make sure you know it. You want to give yourself about 10 to 15 minutes to do this, probably not much longer than that. So you want to make sure that you're studying those pages. So pages 99 to 107. So make sure that you're studying those. So once you finish that classwork, you can come back and I'll review with you. Alright, well assuming that you're watching this now, that you have already done that. So let's go ahead and let's start reviewing. Just make sure that you're covering everything for it. Alright, what do you call the changing of a solid into a liquid? What do we call that? Melting. Alright, what do we call it whenever you're going from a liquid into a solid? Freezing. What do you call that point whenever melting occurs? What do we call that point whenever a substance starts to melt? Melting point. And what do you call the temperature at which the substance starts to freeze? Freezing point. Typically it's the same temperature. It just depends on if you're adding energy in or taking energy out. Alright, what do we call the substances that you can put in a liquid and they will dissolve and intermix throughout your liquid? A solute. Good. Alright, what do we call it whenever you throw in something like a solute and it lowers the freezing point of a substance? What do we call that? Freezing point depression. Good job. Alright, what do we call heat that is hidden? Now, it's still being absorbed or given off, but it's not causing a temperature change. What do we call that type of heat? Latent heat. Good job. Now, what do we call the latent heat specifically required to change a given mass of a solid into a liquid without changing the temperature? What do we call it specifically if it's going from a solid to a liquid? Heat of fusion. Good job. Now, we use that term to go backwards as well, but specifically if I'm asking for a solid to a liquid, that's heat of fusion. Alright, what do we call it whenever you're going from a solid, whenever you're going from a liquid to a gas? What do we call that? Evaporization or vaporization. There are 5 things that affect the rates of evaporation. What are they? Name as many as you can. Right, temperature, surface area of the liquid, strength of the air currents above the liquid, air pressure above the surface of the liquid, properties of the liquid in and of itself. So make a note of all those 5. Hopefully you can list them off really quick. Alright, what do we call some substances, some liquids that just evaporate faster than others? What do you call a substance, or what do you call a liquid that evaporates rapidly? Volatile. What if it doesn't evaporate rapidly? Non-volatile. Good. What do we call it whenever you have evaporation throughout the whole container? Boiling. Great. What do we call the temperature at which a substance starts to boil? So for water, this is 100 degrees Celsius. That's the boiling point. Good job. Alright, there are several things we can do to control the boiling point or to raise the boiling point. What do we call that whenever you're trying to raise the boiling point of a liquid? Boiling point elevation. Now there's 2 ways we can really do this. The first one is you can throw in a non-volatile solute. That'll automatically raise the boiling point. So make a note of that. If I throw in a solute, it'll clutter it up so that way it can't boil at that temperature. So it'll have to increase to a higher temperature. What's the other way to increase the boiling point for a substance? I need to raise that temperature. What's the other way? Increase the pressure. Good job. So what would happen if I were to decrease the pressure? Would the boiling point increase, decrease, or stay the same? the boiling point would decrease as well. It can boil at a lower temperature. But if I were to throw in a non-volatile solute, or just a solute, is how your book introduces it now. If I were to throw in something into my liquid, would the boiling point increase, decrease, or stay the same? It would increase because it's cluttered up now. Alright, which one's large? Oh, first off, what do you call the energy to change from a liquid into a gas? What's that latent heat called? Heat of vaporization. Perfect. Now, what do we call now? Which one is larger? Heat of vaporization or heat of fusion? Heat of vaporization. Why? Because it takes more energy to break those cohesive forces. If you're going just from a solid locked into a liquid, an object that can flow, okay, they're still next to each other, so you still have cohesive forces, but you're just breaking apart how tight they are. If you're going from a liquid to a gas, you have to break apart those cohesive forces. So because of that, heat of vaporization is much greater than heat of fusion. Alright, what do you call it if you're going from a gas to a liquid? Condensation. And we use the term heat of vaporization to refer to the heat being gained or lost from those conditions. We just typically, if you're talking about heat of vaporization specifically, then you're going from a liquid to a gas. But scientists use the same term if you're going backwards as well. Alright. What do you call it whenever you have the rates of evaporation and condensation are equal at a given temperature? What do we call that? Vapor pressure. Good job. Alright, what do we call the temperature at which, no matter how much pressure you put on a substance, it will not stay a liquid. It's going to boil. It's too hot. What do we call that temperature? The critical temperature. Good. Alright, thinking about the parts of a heat pump. What is the most important component? The most important part? Refrigerant. Great. What is the part that compresses the gas to a very high temperature of a heat pump? Compressor, so that at least makes sense. What's the part that allows it to cool down? And so because of that, it'll turn back into a liquid, or it condenses. So what do we call that part? Condenser. Alright, what do you call the part whenever it drops in pressure? And so because of that, the liquid can now expand into a gas. Whenever it does that, it absorbs a lot of the energy from the air around it. Evaporator. Good job. Those are the three parts of a heat, well, three parts, the major parts, and there's the fluid, refrigerant on the inside that's flowing around. Refrigerant is the most important part. I want to keep calling it reactant, and that's not the right term. Alright, so if you realize now that you need to study a little bit longer, you can go ahead and study a little bit longer. So pause the video if you need to, but don't listen to the rest of the video until you're ready to go ahead and take your quiz. So if you want to take another minute or two to go double check a couple things, page 109 to 107, go ahead and pause the video, but don't listen till this next part until you're ready to take it. So go ahead and take out a piece of paper and a pen. You don't need your calculator today, but you need to clear up everything else. So your textbook, your cell phone, calculator, all of it should be cleared and put away. The only thing you should have out is a pen and a piece of paper. You don't need a cover sheet for obvious reasons, but make sure you have that pen and piece of paper out so you are ready to take your quiz. So like how you did on Monday, make sure that you have everything else off your desk and that you're ready to go ahead and take this. So clear off everything, put everything else away. You should only have that pen and that piece of paper on your desk. So again, if you just came on, so a couple of people have logged on, if you're ready to take your quiz, go ahead and you can go ahead and take it, but make sure that if you're not ready to take it, if you realize you need to go get something or you want to pause the study, pause the video. But make sure you have your name and date at the top so I know who you are whenever I print this off later, and then label it 1 through 10. Again, only listen to this part if you're ready to go ahead and take your quiz. Alright, well let's go ahead and let's get started. So, number 1, what do you call the changing, what state is that when you're going from a liquid into a solid? What do we call that state change from a liquid to a solid? Liquid to solid. Alright, number 2, what do you call this phenomenon whenever I put a solute into my liquid and I lower the freezing point? What do we call that phenomenon whenever I'm lowering my freezing point? What do we call that? Alright, number 3, what do we call the type of heat whenever it's absorbing or giving off energy, but you don't see it with the temperature change? It looks like the heat is hidden. What do we call that type of heat? So don't write heat of fusion or heat of vaporization. What's that term that means that, okay, it's absorbing or giving off energy, but you don't see it with a temperature change? What type of heat is that? Alright, number 4. What do you call the change of a substance from a liquid into a gas? So if you're going from a liquid to a gas, what do we call that? What state change is that? Number 5. There are 5 things that affect the rate of evaporation. Name one. Pick the one you can spell. So, factors that determine the rates of evaporation. There are 5 of them. Pick one. Number 6, what do you call a liquid that evaporates rapidly? What do you call a liquid that evaporates rapidly? Number 7, alright, if I increase the pressure on a liquid, will the boiling point increase, decrease, or stay the same? If I increase the pressure on a liquid, will the boiling point increase, decrease, or stay the same? You have a 1 in 3 chances of guessing correctly. Alright, number 8. If I throw in a solute into my substance, so I add a solute, will the boiling point increase, decrease, or stay the same? So, if I throw in a solute, will the boiling point increase, decrease, or stay the same? Number 9, which one is typically greater? Heat of fusion or heat of vaporization? Actually, which one's always greater? Heat of fusion, heat or vaporization. You have 50-50 shot here. So heat of fusion or heat of vaporization, which one is always the greater value or has the greater amount of energy? Heat of fusion, heat of vaporization. Alright, number 10. What do you call it whenever a gas changes into a liquid? What do you call it whenever a gas changes into a liquid? Alright, if you need something repeated, be sure to rewind back and to go back to listen to those particular sections of the quiz. Be careful not to go back too far though, you don't want to listen to the review accidentally. So just be careful to rewind just a little bit to hear some of those questions if you need them again. Once you finish taking it though, go ahead and put it off to the side so you can give it to your mom or dad or whoever is proctoring you. So make sure you give it to them later so that way they can send it in to me so I can go ahead and grade it. You can go ahead and put that away for right now. Alright, we left off talking about vapor pressure yesterday and talking about heat pumps. Oh, my computer fell asleep. Hang on. Alright, so we ended up yesterday talking about vapor pressure of water specifically, but then also vapor pressure of other objects. Okay, well, liquid specifically. Alright, so talking about, if I have a substance like water, and if I decrease the vapor pressure, that means the water can evaporate that much more quickly for it. So, vapor pressure, this is the term we use to say that you have condensation and evaporation are occurring at the same time. They are equal. Now, for different substances, they're going to have different vapor pressure. Water is kind of the easiest one to work with because water, at given temperatures, is going to have more energy. So, the vapor pressure will start to increase with the idea of, at a given temperature, how much pressure or how much will the water evaporate until the rates are equal. So at 100 degrees Celsius though, that's whenever the rates are equal, and since it equals the since it equals the atmospheric pressure, that's whenever the pot can start to boil now, because not only are the rates equal in that regard, but now there's enough to overcome atmospheric pressure at all, and it can go ahead and fully boil and evaporate that way. So that's the idea of vapor pressure, where this whenever the condensation rates and evaporation rates are equal. Now, since there's atmosphere pushing down on it, you might have a little bit of evaporation, but you're not going to have full-on boiling until you have the vapor pressure be strong enough to overcome atmospheric pressure. That's why we say for normal atmosphere, water boils at 100 degrees Celsius. That's if it has enough energy now to overcome and be strong enough to go ahead and to evaporate out entirely for it. So you have to increase the pressure to 224 kilopascals if you want water to boil at 374 degrees Celsius. Now there is that point whenever it has so much energy that that's its critical temperature, and it doesn't matter how much pressure you put on it, it's going to boil. It has too much energy at that point. I knew I had this slide somewhere. So this is showing you the vapor pressure of selected liquids. So again, all of these are at 25 degrees Celsius. So it's showing you here's the vapor pressure at selected liquids. So at 25 degrees Celsius, that's about room temperature. This one has a vapor pressure of about 7.9, I'm just giving 2 sig kilopascals. This one would be a liquid. Now, this is whenever its condensation and evaporation rates are equal. It doesn't have enough energy to boil, but it still has vapor pressure. 25 degrees Celsius, it has 66.9 kilopascals of pressure. So because of that, it'll still evaporate, but it's not going to full on boil. This one, it has 350 kilopascals. That's enough pressure to go ahead and evaporate. That's why isobutane, like how we looked at yesterday, wants to evaporate and has so much pressure put on it on the inside of the aerosol cans, because it wants to evaporate at room temperature. This is enough pressure to where it can go ahead and evaporate. As a side note, just kind of thinking about it, should you ever then, if you have an aerosol can with isobutane on the inside underneath this much pressure, should you ever put an aerosol can into the fire or throw it in a bonfire? No. Anyone that's done that, you might know what happens. What do you think would happen if you were to throw a can underneath this much pressure into a fire or keep it somewhere really hot? It'll explode, because not only do you have the gas on the inside, it wants to turn into that gas already. If you give them more energy with heat, they can't handle it, and it can cause your aerosol can to explode. So do not do that. It is dangerous. So make note of that. That's for vapor pressure. So just to make sure that you got it, vapor pressure is whenever condensation and evaporation are equal, and if you want your pot to boil or your liquid to boil, you have to give it enough, you have to increase the vapor pressure, that equal rate, until it's high enough to overcome the atmospheric pressure. So that's why for water it boils at 100 degrees Celsius, it's going to have enough energy to where the vapor pressure equals the atmospheric pressure, so now it can go ahead and boil on out. Alright. So we looked at this with the parts of the heat pump yesterday. So remember, there's that high pressure region, and then there is that low pressure region of the heat pump. In the high pressure region, you have it to where typically in the fridge, it could be down here in your model, it could be a little bit different, but you have the compressor where it compresses or pushes your gas, well, your gaseous substance that wants to remain a gas, but it compresses it so much where it forces it to be in that liquid state. Now it doesn't want to stay there. So whenever it does that, whenever it pushes it all together, according to a Montan's law, the temperature will increase. So that's why whenever your compressor compresses the gas, it'll give off heat. Now remember, what direction does heat always flow? Does it go from warmer objects to colder objects, or colder objects to warmer objects? Right, it always goes from warmer objects to colder objects. So because of that, if you have a hot liquid, that it'll give off the heat into the air around it. Also come the bottom of your fridge typically has that warm air coming out of it. So that's what it's talking about with the principles of refrigeration. At the top of page 109 is a side note. This helps you to see it that way as well. Whenever the gas is compressed, the temperature rises. When the gas condenses, whenever they allow it to condense, it's giving off that latent heat. So not only is it gaining heat because it's being pushed together, as it gives off that heat to condense into the liquid, that's whenever it's losing heat or giving off heat. So that's whenever it's heating up the air around it. So there's both things that are affecting it. So whenever you're having it compressed, that's whenever it gets to a really high temperature, and then in the condenser, it lets it condense now into the liquid version because it's still under pressure, but now it's losing heat to the air around it, and so because of that, it condenses or turns into a liquid. So eventually, it'll go up into the evaporator. So it goes through a small opening and then up in here into the evaporator section. So the evaporator, that's whenever it allows it to evaporate. It drops the pressure so that way your gas can now expand. As it does that, it cools it cools the air around it, because the gas, as it expands, according to Charles' law, if you want to think of it that way, that if you have the volume increase, the temperature also increases as well, because it is absorbing all the energy from the air around it. So with the evaporator, it has a drop in pressure, so the air changes instantly into a vapor, absorbing the energy as latent and cooling the air around it drastically. That's what come in your book, the color is like a blue color, because it's absorbing all the heat around them, and so that's how the air around them gets really, really, really cold. So since it's going from a liquid to a gas, that's how it's absorbing all that latent heat to change from one state to another, and so it cools the air around it. Typically, your refrigerator has a fan here or something to blow it across your objects in your refrigerator, so that way it blows the cooler around. So it'll go to the compressor again, and then go through the whole process all over again. Your compressor is typically hooked up to electricity, and that's how come your fridge has to stay plugged in. Alright, so refrigerators and air conditioners are a common example of this. We've already talked about this already. Heat pumps is another one with kind of like a heat or an air conditioning unit in your windowsill. You might have seen this with an air conditioner before. This model shows it also as well. Some models, they can actually be reversed, where they can either generate heat or generate air conditioning. So some of them, they are designed so that way they can actually go both ways. It just depends on your particular model. So this is a kind of like a window model for an air conditioner. So it's showing you that, okay, you have over here the warm air in with the compressor. So the compressor forces the refrigerant gas together and raises the temperature. And then as it cools in the as it gets in the condenser and cools, it goes to its liquid stage. So it's giving off the heat to the air around it. And that's how come they drew these coils as an orangey red color. So it turns from a gas to a liquid. Whenever it does that, it gives off heat, so it warms the air around it. So also you might have a fan on this side blowing the hot air out of your air conditioning unit. So once it goes through the evaporator though, it allows it to drop in that pressure. Whenever it drops in that pressure, it expands back out again. In order to go from a liquid to a gas, it has to absorb a lot of energy. So whenever it does that, it cools the air around it. So again, on this side, it has the fan to blow that cool air into your room, and then it goes back through the whole process all over again. So again, just like the fridge, it's just a different kind of sideways model. So sometimes people understand this one a little bit easier. So compressor compresses the gas really close together, heats up in the condenser. It allows it to give off that heat so it condenses into a liquid. And then when it goes through the small opening, it allows it to expand back out, so it evaporates. Whenever it does that, it absorbs a lot of energy, so that way it cools the air around it. So do note the different parts of the heat pump, but do note that the most important part is the refrigerant. That's the liquid that's turning into a gas or into a liquid, and that's what's causing to either give off a lot of heat or to absorb a lot of heat. Alright, so just make a note for we talked through a lot of that yesterday, just making sure that you understand it and that you got it. Alright, so wrong direction. No? I must have put it in the wrong spot yesterday. Alright, so your book talks about the last couple of things before we finish up this section. So sublimation and deposition. Alright, so we've already talked about if you're going from a solid to a liquid to a gas to a liquid, and a liquid to a solid. So there are 3 state changes. So if you're going from a solid to a liquid, what are you doing? Melting. What if you're going from a liquid to a gas? Evaporating. What if you're going from a gas to a liquid? Condensation. What if you're going from a liquid to a solid? Freezing. So your book points out there are two kind of exceptions to this rule. Some substances, they can skip the liquid phase entirely and jump from a solid to a gas or a gas to a liquid. They can basically shortcut and jump around that whole stage entirely. All right. If it goes from a solid to a gas, this is whenever you're going from a gas to a solid. I drew a blank on what I was talking about. If you're going from a gas to a solid, that is deposition. If you're going from a solid to a gas, that is sublimation. So mark those two. So for the first one, you're going from a solid into a gas. That is sublimation. That's what the one your book's showing you with dry ice. If you've ever held dry ice before or worked with dry ice, you'll know that it's really, 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 really cold. That is frozen carbon dioxide as a side note. So dry ice or frozen carbon dioxide, this is the stuff that you breathe out as a side note. So carbon dioxide, you cool it down to a very cold temperature, it will turn into solid carbon dioxide. Now typically at room temperature, carbon dioxide is a gas at room temperature. But you can cool it down and you can make it be frozen. So your book points out that this one is a very, very, very cold substance. It'll sublime or jump from a solid to the gas at negative 78.15 degrees Celsius or greater. So you have to cool it down to a very cold temperature. Also, the reason why you got to be careful with dry ice, if you hold it in your hand and then wrap your fingers around it, it can actually kind of burn your hand because it's absorbing the heat so quickly from your hand because it wants to jump from that solid to the gas state. And also it looks kind of foggy around it, so it's showing you dry ice subliming. So that's whenever it changes from a solid to a gas. It's jumping the liquid stage entirely. It's jumping straight from a solid into that gaseous form of it. So So that's dry ice. So if you ever work with dry ice, or if you have dry ice, you gotta be careful of it. You can touch it and you can hold it in your palm as long as you hold it and you don't have a big chunk putting pressure on it. But it'll start to boil or evaporate just sitting there in your palm because it's the dry piece and it's changing into that liquid form. So you can do that as long as you're being careful, but if you wrap your hand around it, it'll start sucking the heat out of your palm and it feels like it's burning you because it's pulling all the heat out of your palm basically, and it can hurt your cells and your skin. It kind of gives you like a burn. So you gotta be careful with that because it's taking the heat out too quickly. Alright, technically it's more like frostbite at that point, but it hurts like it's burning you, so don't do that. Alright, deposition is the opposite. That's whenever it's going from a gas into a solid. Frost is an example of this. Now keep in mind, frost is just frozen water, but in some cases, with the water vapor in the air, because it's in the air, if the air cools, in some cases, it can skip that liquid state entirely and form these frost crystals directly if it touches an object. So just make a note of that this is an example of sublimation. This is whenever it goes, nope, that's dry ice. Deposition is whenever it goes from a gas to a solid. So make a note for that one. That's whenever you have a sentence goes from a gas to a solid, deposition. I forgot which one I was talking about. Deposition, gas to a solid. So like frost. This is whenever the water vapor cools down so far that whenever it touches an object, it'll freeze onto it. This will come you get frost on your window panes or on blades of grass because it's the water vapor in the air. It's cooled down so much at that point that instead of going into the liquid, it's jumping now into the solid version. Alright, your book talks about the last state of matter. So we have solid, liquid, and gas. Those are the 3 common states on Earth. There is a 4th state. We actually think this state's the most abundant state if you're talking about the entire universe altogether, because this is what we think stars is made of. Now this one does not exist on Earth that well. I'm going to turn off the lights in a minute so you can see this a little bit better. But this is whenever you have a substance get so much heat on the inside of it that it no longer exists in just the gas stage. It'll break apart into those ions and be charged particles floating around in the air. This is one reason why if you pull a electrical socket out of the wall slowly, careful if you do this, please don't. But if you do, you'll notice sometimes that there's a spark. That's because it's creating ozone or the charged particles of oxygen right there. That's how it smells kind of a little bit weird, like static electricity. That's the reason why it's creating a little bit of ozone, and that is a type of plasma. So we see it mainly with lightning, but that's pretty much it. So just make a note, this is whenever the molecules disintegrate and break apart into their charged particles. So I'll show you this in just a second. I gotta go with the lights though. Alright, I'm going to turn off the screen because that'll make it a little bit easier to see. Okay. So it should show better on the backdrop. Okay, I think my shadow is helping out with it as well. Okay, so this is an example of a plasma globe. So there is argon gas on the inside of this plasma globe. Now, I'm not heating it up to a super high temperature, but I have it plugged into the wall because I'm overloading it with electrons, and so it makes the argon gas on the inside turn into plasma with the idea of it doesn't like the extra electrons, so it's kicking them off. So it's doing the same thing with charged particles, just a different way of making it. So, yeah, I don't know how well you can hear it on the camera. I'm hoping not too well, but sometimes the camera and the microphone picks up air and other things in the room. But it's making a very high static electricity sound that's bothering me a little bit. So if I touch it, I don't know if you can hear it or not, but it's making that sound. I'm hoping it's not picking it up too bad for you. But that's the reason why it turns into plasma. Now, whenever I touch it, it's trying to get rid of the electrons that it's giving it to my fingertips, so it's not hurting me, and that's fine. That's the reason why you can see plasma like this. It's in that charged particle state. Now, typically, we see these on Earth with lightning strikes or high energy areas, like if you take the electricity out of the wall, you can see that spark. That's an example of the ozone being formed there. So ozone is a type of charged oxygen. So make a note though, this special state of matter exists whenever the temperatures are too high for matter to exist in ordinary states. This is plasma. You can also overload it with electrons, and that also works. We'll talk more about electricity with this later on. This is another way to get plasma. So again, this is an example of a plasma globe. So this is what we think stars are made of because they're at so high temperatures. We think that they are probably made up of plasma. If you factor in all of the plasma, if you factor in all of the stars in the universe, plasma is technically the most abundant state of matter on the entire universe, but on Earth, we don't have it that much. Now I'm gonna go ahead and unplug this because it's still making that high ringing sound and I don't like it. So I'm sorry, plasma globe. So that'll help it to cool down as well. Alright, move the light again, so that I'm not sitting in the dark and talking in the dark. Alright, so that is everything then for your exam coming up. Book is this handy chart of states, of changes of state. Make sure you note that. So melting, this is whenever it goes from a solid to a liquid. Freezing, that's whenever a liquid goes into a solid. Evaporation, that's whenever the liquid goes into a gas. Boiling, that's whenever you have it evaporating throughout the whole liquid. Condensation, gas goes to liquid. Sublimation, that's whenever solid changes into a gas. Deposition, gas changes directly into a solid. So make sure that you note all of those things about it. And so in order to get you started on your exam, I'm going to go ahead and give you your homework. We're going to have a Zoom class on Monday, so have your parents check their emails for it. But we're going to go over a lot of the math on Monday. So because of that, your homework is going to be math heavy. So I want to make sure you know your equations and you know how to solve them. There goes a piece of chalk. Alright, so your homework for tonight. Go ahead and get out your assignment pads. On page 112 in the chapter review, you're going to do the apply 2 and 4. So on page 112, apply 2 and 4. On page 179 in the chapter review, you're going to do 2 and 3. On page 79, 2 and 3. On page 69 in the chapter review, you're going to do 3 and 4. So on page 69 in the chapter review, 3 and 4. Alright, I'm going to give it all to you again because I know that was probably very confusing. So you're doing just a lot of the application and the math problems in the different sections and the different chapter reviews. So to help you get you ready for Monday. If you get stuck, try to solve it, try to figure out and write down all of your math steps. If I ask you, how did you get that, how did you get that answer? If you ask me, Miss Morris, how did I get this answer? Unless you write down what you did, I don't know. I'm not a mind reader. And since I can't see your paper, you're going to have to write down what each step was so I can help you fix it. So don't just write down an answer and then tell me, I don't know what I did. Well, I can't help you. So make sure you show all of your work so that way on Monday, whenever you get stuck and you have to ask me, I don't know what to do, I can help you fix it. Alright, so on page 112, it's application 2 and 4 on page 112. Page 79, application 2 and 3 on page 79. On page 69, application 3 and 4. On page 79, 3 and 4. Don't forget the final draft of your background is not this Monday, but the next Monday. So October 12th, don't forget this is the final draft of your background paper. Alright, so have your parents email me the quiz as soon as they can.